background, please. All right, page 33. Here we go. Now, particle accelerators. We could have done particle accelerators in Unit 3. Brendan, you're feeling a bit too safe in this classroom. Because all you're doing is, well, you can accelerate them in an electric field and you can bend them in a magnetic field. But the reason why they do it in Unit 4 is because particles are very, very small, and so it's very easy to get them travelling very fast. And when they travel very fast, we've got to do the whole relativistic considerations. So that's why we do it now. And I'm basically going to tick two boxes. We're going to do particle accelerators, but we're also going to consider relativistic effects. Okay? So, on this page, I'm going to show you the workings of a mass spectrometer, which is doing 3 separate things. And they're all interesting, so pay attention. Part 1 is going to be a LINAC. Now, that is a linear accelerator. Essentially, what you do, you take your atom and you ionize it. So, for example, I'm going to use chlorine. It creates a 1- ion. We're going to accelerate that negative ion across a potential. Now, here is the problem. Our chlorine are going to have isotopes of differing mass. And we might want to separate these guys out. All right, so we've got to speed them up first. So they're going to speed up and they travel through this little aperture. All right, so they accelerate, and just below we can use the old school work done equals QV, which equals half mv squared if we're travelling less than 10% the speed of light. If they're going greater, we've got to do the old gamma minus 1 m0 c squared. But we can do that, that's easy. But here's the problem. That capital V for voltage, that tells us the maximum attainable energy. It doesn't mean that they all get QV. It just means that the most energetic ion will have an energy equal to QV. Some will get a little bit less. All right. So here is the problem. You're going to get different masses, all with different velocities. Different velocities entering into section 2. And what we need to do in section 2 is select only those with a certain velocity. And this is a really interesting way that they do it. And I don't think Brendan's going to understand because he's not paying attention. Good. So, in section 2, here is our charged particle. Well, first off, let's try and bend our particle, let's just say downwards, by establishing another. In fact, I'm going to go the other way. Let's try and bend this bad boy upwards by creating a voltage across these plates. Now, in that way, there would be an electric force equal to, I don't know, E times Q, okay? That would want to bend it upwards. But at the same time, let's try and bend him downwards with a magnetic force. So I'm going to produce a magnetic field, and I'm going to bring in my friend, we haven't used him for a while, the Lorentz force. I'm a negative charge travelling that way. Let's just use the red arrow to represent velocity. So my thumb points left. I want my magnetic field to push this bad boy downwards. So let's just draw a uniform magnetic field going into the page. Okay, so in this region, let's draw our uniform magnetic field going into the page. And I'm just going to leave some room because I need to write that the magnitude of that force is equal to VQB. Okay? Now, just down the bottom here, highlighted a lovely orange. Look what happens. I've got a cancely, and we can rearrange that at just the right velocity, only those that will travel, they'll come out with a velocity that's the electric field strength divided by the magnetic field strength. And we can make magnetic fields, electric fields up in the order of 10 to the 4, 10 to the 5. You can have a high voltage across a small region. That's easy. So we can get, all you need to do, on the side of your machine, you have an electric field dial, crank it up. You have a magnetic field dial, drop it down. You know, you can vary it so that I know that all the particles are going to travel through at that velocity equal to E over B. And here is why. If I was traveling too fast, let's go too fast. If I was traveling too fast, then I would get bent downwards. Why? Because this force, the magnetic force, is the only one that's dependent on V. And if my velocity is too big, then my downwards force is greater than the upwards force, and I would accelerate downwards. And I would smack into the wall, and I wouldn't travel through. Let's go the other way. If I was traveling too slow, now the opposite occurs. Now, if I'm traveling too slow, then the Lorentz force is now reduced in magnitude, and the electrical force upwards is now greater, and the particle accelerates upwards. This is a really cool thing, because the ones that just have the right velocity equal to E over B, travel through, okay? Now, that's the velocity selector, a really cool way to make sure that every single isotope, no matter whether they're a big isotope or a small isotope, is going to come through and they're all traveling at the same speed. That's important because we need to make sure that V is a constant in this next part, all right? Now, section 3, I'd like you to draw a semicircle like so. And we're going to bend these bad boys in a magnetic field. And you guessed it, it's the same direction. So let's just draw a somewhat uniform magnetic field in this region. Region 3 is where our mass spectrometer is. Okay, now, we said that I've got chlorine, and the periodic table says that chlorine has a weighted atomic mass of 35.45 or whatever the hell it is. That's the relative weighted average of all the naturally occurring isotopes of chlorine, yeah? But we know that there's a 35 and a 36 and a 37. So here's the thing. In this part, we're going to do the whole, down the bottom here, we do that the magnetic force, which is equal to QVB, is going to produce the centripetal, which is mv squared on r, and we do a cancelly and a cancelly, and we get this lovely equation. Now I'm going to write it, the Q on m equals V over BR, okay? Now I'm going to write it like that, but in your data sheet, let me just write him over here. In your data sheet, in your data sheet, you have, and I've got it right here, you are spot on, and the title of it is the something, the radius, I lost it. Particle motion in a magnetic field, R equals mv over qb. That's what you have, which is nice for a number of reasons. I'm going to draw in things that are constant. We know that all the particles have the same velocity. We also know that all the particles have the same charge. They're all chlorine -1 ions. They're all in the same magnetic field. The only thing that's going to vary is they might have different masses. Now have a think. If you have a heavier mass, you have more inertia, you have more resistance to change. And so your acceleration is going to be less, and so your radius of curvature is going to be greater. Now that agrees that m is proportional to r. If m goes up, then we would expect the radius of curvature of our circular path to also increase. So from that, I mean, I'm just going to grab it from here, m proportional to r. So if your chlorine 36 atom is about, 3% more massive than your chlorine 35, you would expect the radius of curvature, and hence the diameter of the circular path, to also be 3% greater. Okay? And you can see it there, radius directly proportional to mass. That's in your data sheet. So, let's sketch a couple. Let's sketch our good old chlorine 35, nice semicircle there. Now let's draw our slightly more inert, slightly more resistance to change, slightly greater radius chlorine 36. And then again, slightly more inert, slightly more resistance to change, chlorine 37. Now all we need to do, we could put little buckets there and catch them like golf balls, or you could have an electric detector like Brendan Dong and Robert Lee, that when they get smacked into by chlorine atoms, chlorine ions, it might generate a small electrical impulse that you can start counting. Okay? And this is what they do. They're counting little flashes of electric charge that strike these little detectors. Up here, you've got a little graph that I'd like to quickly sketch. This is the kind of result that you get. Intensity over either radius or mass, because we saw that they are directly proportional. Here's what you get. You get nothing, 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 and you get a massive spike, and that might be chlorine 35, and then you might get nothing, 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 and then you might get 36, and then nothing, 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 and then you might get 37. And then by comparing the relative intensities of the peaks and how far apart they are, you can determine how many different isotopes of what mass and in what relative proportions. So you're just looking at how big the spikes are related to the total. So that's how they do their mass spectrometry. They can say this sample had 3 isotopes of chlorine, 40% was 35 and 20%, and then I'm bad at maths, and then 70% was 37. They can figure out the relative abundances. Okay? If we go back down to our data sheet, the reason I leave these... Oh no, that shouldn't have done that. I wanted it to do that. This Q on M is known as a charge to mass ratio. And all charged particles have a charge to mass ratio. You're either going to have a charge of 1 or 2 or 3, depending on your ion. An electron has the highest charge to mass because it has a fundamental charge of 1, and its mass is like 1,200 times lighter than a proton. So a hydrogen ion would be Q on M. If you took your electron, the Q on M is like 1,200 times bigger. So it has a much, much higher charge to mass ratio. But that's the thing. Different elements, different atoms will have their QM ratio. So let's say we're going to throw in let's throw in oxygen. We're going to try and detect oxygen. It's going to have a different QM ratio. And so we might have to tweak our magnetic field and our velocity to be able to detect something that has a QM ratio, maybe oxygen 14 and 15 and 16. So you change your dials. Maybe the radius is set. Maybe your mass spectrometer has a fixed radius that your detectors can't change where your detectors are. So maybe we can change the velocity in the magnetic field. All right? You put your oxygen in here, you ionize it, you accelerate it linearly, your velocity selects so you know that every single oxygen isotope has the same velocity, and then you allow them to curve around based on their physical properties. Remember, this is a separation technique based on physical properties of mass. All right? So the more inert isotope is going to bend over a greater radius. Really fun stuff. Okay? Okay. Now, we are nearly there. We're nearly going to talk about relativistic effects. And this lovely equation is not in your data sheet because remember, some physicists argue that you can't measure the mass of something that travels past you at half the speed of light. You can only measure its rest mass, and it's actually momentum that increases. So don't worry. Here is a cyclotron. So we looked at a LINAC. A LINAC linearly accelerates your particle in an electric field. Okay? This is a really cool way of reusing an electric field. Because have a think. if your particle accelerates up to, I don't know, half the speed of light, it's going to be really far away from you. So a line arc is going to have to be hundreds of meters or even kilometers long. Well, maybe that's not feasible. Let's put this bad boy into a circle. Cyclo. This is going to be a cyclotron. So here's what we're going to do. I drew this diagram. I probably could have drawn a better one, but hey, let's start with our purple ion, which is positively charged. Let's accelerate this positively charged particle across an electric field. Okay, so there's a voltage across this electric plate, and at the moment, let's just say it's positive and it accelerates it towards the negative. All right, so when it accelerates across the plate, it gets a whole lot of QV. It gains a QV multiple of energy. So it's traveling with a certain velocity. Would you agree? Yes. Then, when it enters the, let's just say left and right, these are called Ds. Think of like a pill, like a tablet, and you've snapped the tablet in half along the middle, and you've got these two semicircular Ds, okay? And through these Ds is a uniform magnetic field. Let's bring in our friend the Lorentz right-hand rule. So thumbs pointing in the direction of travel because he's a positive charge. Fingers are pointing down. So this sucker is going to travel, from our point of view, anti-clockwise. Like that. Now, in the time that he went like that, we need to flip the electric field. If we didn't flip the electric field, if this was still positive, then it would be repelled. And it would lose all of that QV. And it would end up stationary. You get a positive QV and then a negative QV. So we need to flip it. Let's give it another QV. So away he goes. He races across. He gets faster, doesn't he? Now, if you're going faster, the equation on the previous page was R equals mv on QB. Oh, look. A faster particle travels in a greater radius. So, there he goes. Greater radius. Let's flip the electric field again. Get him racing across. He now gets 3 QV. Greater radius. 4 QV. Even more speed. Greater radius. Goes. You can see what's happening. The particle is starting to spiral outwards from the center. Every time he gains speed, his radius of curvature increases. And so eventually, you can allow him to come out and smack into whatever you want him to. And the amount of energy is going to be n multiples of QV. So, you might have this thing flipping backwards and forwards 100 times. As it spirals its way out from the center, it might gain 100 lots of QV. Okay? And so the first one of these bad boys that was made by Ernest Lorentz in the 1934s. No. Something's wrong with my laptop. That now when I try to press Mozilla, it just opens a new Mozilla. You're a piece of crap. Restore all windows. Thank you, you stupid. Ernest Lorentz. Where is he? There he is. I don't know. Here's the first cyclotron. Hang on. I want to go down a bit. The history of it was that the first one was 4.8 MeV and it was 70 centimeters wide. And then you got up over the next 10 years, you got up to 16 MeV that ended up being 1.5 meters. So the more energetic the particles, the bigger this machine had to be. There's a reason for it, and we'll explain why in a moment. Anyway, I thought, please have a read of this wiki page on the cyclotron. Thanks, 15 separate. No, thanks, an extra OneNote. No, thanks. Something's wrong with my laptop. I don't know what it is. Still better than a MacBook. Yeah? Now, there was once a question about, with what frequency do we need to flip this electric field? Now, the frequency that we have to flip the electric field is basically the time that particle takes traveling in a semicircle. Okay, so here's what we're going to do. We're going to do our old mv squared on r, which is produced by the q, the v, and the b. I don't know why I'm deciding to put my vectors in. We'll do our cancely. No, that's too much cancely. And let's just get v in terms of a q and the b and the r up the top, and that can become an m. All right. Now we'll do a little side mission here. We need a v equals 2 pi r on t, and we know that t equals 1 on f. So we could do v equals 2 pi r f, our friend that sometimes comes in handy, and he will here. We can now equate 2 pi r f equals q b r on m. Watch this. Q b r on m equals 2 pi r f. Can we cancel? What can we cancel? Yeah, look at that. That's really cool. What it tells us is that the frequency that this thing is moving, which is also the frequency of our alternating voltage, is equal to QB over 2 pi m. Isn't that lovely? That's what we can then set our frequency to of our alternating voltage. Okay? So, do we know the charge of our particle? Yes. Do we know the mass? You betcha. Have we got our magnetic field set? Absolutely. 2 pi? Why not? You just set your frequency and then out comes this stream of particles because everything is working in synchronicity. As the particle travels around, the voltage flips. Okay? It's like pushing a kid on the swing at exactly the right time. But look at that. The radius of curvature doesn't matter. This tells us that the inside slow-moving first turn, travelling at a slow speed with a slow radius, is going to travel it in the same time as our fast outside curve, a greater radius but at a faster speed, directly proportional. They're all going to travel at the same time. And so you just go flip, 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 and out comes boom, 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 boom. A constant stream of energetic particles. Isn't that lovely? Yes. Yes. Looking for a nod there. So this is what Ernest Lawrence, I think, got his Nobel Prize for making these bad boys, because then you can put little kids in front of them and irradiate them with radiation. You think I'm joking? Turns out I can't show you. Restore all windows. Where's that poor little kid? Oh, he's not there. Hang on. Here he is. There he is. Poor little kid. He's got a tumour, so let's just bombard him with like high energy particles. First patient treated for retinoblastoma. Gordon's right eye. Okay. Eventually. But I don't know by what cause. So, an extra OneNote? Sure, why not? Thanks. No thanks. Let's continue. This, of course, only works for non-relativistic speeds. And in the last 10 minutes, we are going to look at an example where when a particle gets really fast, its momentum increases. And if its momentum increases, it becomes more inert. So a classical model says you're going to curve at this, but a relativistic particle has more inertia, it's got more mass, and we find that its radius goes up. And so, have a think. Einstein's working out stuff in the 1920s, and Ernest Lawrence said, thank you very much, I can now apply this to getting particles really fast. So, let's look at the classical model over here, which we know is wrong. But let's just use the classical model. Let's get a proton up to that speed. Now, your data sheet has that the radius is equal to mv over qb. So let's figure out what it should be. Data sheet says that a proton has that mass. Data sheet also says that it has this charge. And so calculator says that if we want to get a proton that fast in this field, then its radius of curvature, Patrick Mahoney, is going to be 2.61 meters. It is not correct. It is not. We need to change. We need to change things up. We need to get real. So, here's what we're going to do. We're going to go hang on. I'm going to go smaller, come closer. We need to get the relativistic mass. Now, the relativistic mass is our old friend, gamma m naught. We need to figure out what the Lorentz factor... Oh, I didn't mean to do that. We need to figure out what the Lorentz... fine, whatever. The Lorentz factor is, okay? Now, really, to get around this equation should really be momentum. Have a look. MV is momentum. So we could say R equals P rel over QB. And then the Physics Society goes, phew, we can use that because P relativistic is going to be gamma m naught V. All right, sweet. So we're happy. Doesn't matter whether you're attaching the Lorentz factor to mass or momentum. It's going to be there, stuck. Let's figure out what it is. So we take our gamma. I'm just going to be tricky and go 1 over square root 1 minus 0.999 squared times R. Really, because really, we're just going to multiply the classical radius with the Lorentz factor. Are we happy with that? If you're not, you're going to have to write all of this again down here. But we're running out of time. So let's just go 2.61. Or R. So that speeds things up a little bit. Turns out the Lorentz factor, when you're travelling at 0.999 c, is 22.4. 22.4 times 2.61. Our cyclotron needs to be 58.4 meters in radius. Okay? So things are starting to get big because of relativity. That is why our most recent particle accelerators have to span the sizes of small countries. They cross into the border of France and then come back. You go, well, what can we change? We can't change the charge. We can't say, proton, I want your charge to be 1,000 times bigger. Great, radius is 1,000 times smaller. Can't do that. We're limited with the strength of the magnetic field. If we get too big, then engineers and workers will get sucked into the machine and turn into a red mist, so you can't do that. The only thing you can do is increase the radius. So, in the last 5 minutes, I'd like you to now consider, if you have the space, here, currently at CERN, protons have been accelerated to 8 nines, then a 7 4. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 7, 4, C. Could you please tell me how big my radius needs to be, given those values, given a proton travelling at that speed in that magnetic field? Tell me how big my particle accelerator needs to be. And since we have the time, let's write it out in full. Let's not cheat. You could tell me that the Lorentz factor is 13,840, but let's do it properly. R equals so we could simply, this is m naught v over square root 1 minus beta squared times qb. I'll just try to tidy things up a little bit. Now, some snarky student here said, you could just go 3 times 10 to the 8, really. It's not going to be significant, but write it down anyway. It doesn't really matter. You're still going to get 3 times 10 to the 8, so really, you could almost get rid of it. But what you can't get rid of is the Lorentz factor. 1, 2, 3, 4, 5, 6, 7, 8, then a 7, 4 squared, times 1.60 10, negative 19, 1.2. So you have to do that. Your Casio FX82 Plus can handle these many decimals. It will calculate it for you, and it will give you the radius of the Large Hadron Collider. No, wait. Large Hadron Collider is a section, one section of the solution.
It's a very big thing.
What do you get?
I got
Maybe, I don't know.
36 kilometers. 36.
Yeah,
Nice.
sounds good.
What about jump roll?
Don't know. But basically, that 1 over 1 minus beta squared, that the Lorentz factor, the Lorentz factor comes out to be 13,840. What did you say we got? Sorry?
36.2.
Okay. Now, it turns out it is a little bit bigger than that. Maybe the magnetic fields in the CERN are a little bit weaker. They don't have much luck with their magnetic fields in CERN. They managed to explode one and it shut the thing down for about a year. Because they got to be cooled down so that they become superconducting, so that they can produce such strong magnetic fields. The slightest amount of electrical resistance, and the whole thing just goes bang and melts and warps, and that's what happened. But I hope you all enjoyed this lesson. Yeah. Cross levels.
2 minutes late.
Yuck. No. Sorry. Oh.
What the heck happened there, sir?